We're going to use R mostly for prediction, but it's a number that is often provided in data analyses, and it's very tempting to use in multiple different ways. So it is important that we are able to interpret it appropriately and not use it in ways that it shouldn't be used. Here are a few words of caution. You know that you must not draw causal conclusions simply based on association. Correlation only measures linear association. It doesn't do anything more than that. And of course, association doesn't mean causation. A classic example that we often use is if you look at a population of children from kindergarten through high school, then shoe size and reading ability are positively associated, and so there's a positive correlation between the two. But if your child isn't reading well, are you going to go out and buy them bigger shoes? Is that going to do it? No, of course not. The confounding factor is age. It's older children who are both bigger and read better. These ideas that we've had from the very first week of 8.1x are still there, and we have to be careful. When you see a positive correlation, you are seeing a linear association in a positive direction, and that's all you're seeing. If you want to conclude more, then you have to do more work and look at all the other factors that are relevant. It's also important to draw a scatter plot before you compute R. In particular because nonlinearity and outliers, both of these can affect your interpretation. Here's an example of a table called nonlinear. We're drawing a scatter diagram of x and y. X and y are clearly related. We computed y as the square of x. If you calculate the correlation, so you're going to use our function, name of table, label of x, label of y, you get 0. These two variables are uncorrelated. But would you say that they are unrelated? Certainly not. They are closely related. If I know x, I know y exactly. Y is equal to x squared. Y is a function of x. So uncorrelated means not linearly associated. For such a scatter plot, I wouldn't compute R. There isn't a linear association. That's very apparent. So R isn't going to help. And the moral of the story is, first draw the scatter diagram, and then compute R. Visualize, then quantify. Outliers also can have serious effects. Here is a scatter diagram that shows a correlation of +1. And here are those same points, but with an additional one. That's an outlier. What happened to the correlation? Let's take a look. The table is called outlier, and the variables are called x and y. So we will do correlation of the outlier table, and it's 2 columns, and we get 0. We went from a scatter diagram that had a perfect correlation of +1. We threw in 1 point, and that dropped the correlation to 0. Outliers can have a very serious effect on correlation. Again, draw the scatter diagram first. If there are outliers, they might affect your correlation quite significantly. So what you should do is look hard at why they are there. People are tempted to leave them out and look at the rest of the points, but don't leave them out. They might be the most interesting points. You should first check whether you have some kind of calculation error, and that's some silly reason why the points are out far away from the rest of the data. But if not, then those are interesting points. And you might want to look at them separately from the others, but you must look at them as well as the others. So if you leave them out in your analysis of the other points, that's okay, but then you must come back to them and explain why they are different, or try to understand them. One other aspect of correlations has to do with making sure that you look at the individuals on whom the variables are measured. Correlations that are based on grouping or aggregating data are called ecological correlations, and they can be quite misleading. Often they are artificially high. This will become clearer if we look at an example. The table SAT 2014 contains SAT scores, or average SAT scores, in the different states. Let's look at the table and then we'll see exactly how exactly what has been measured. There are 51 points. Each point corresponds to a state. And also there is the District of Columbia, so DC, and that's why there are 51. For each state, these are 2014 scores. There is the participation rate in the exam, that is the percent of high school seniors that took the test. The average critical reading score, the average math score, the average writing score, and then the combined score in all of these three elements. The SAT has changed since then. These are the SAT scores as they were in 2014. Let's draw a scatter diagram of the critical reading and math scores. Look at that. Almost linear, very, very tight. And indeed, if you compute the correlation, you have 0.985 almost, extremely high. And this sure makes you feel like if you knew somebody's critical reading score, you could almost without error say what their math score is going to be using these data. But that can't be right. You can't be that good. The relation can't be that tight between critical reading and math. Yet here it is. And the problem that we are facing is that in our heads, when we say we are trying to predict math scores based on critical reading scores, we are, of course, thinking of individuals that take these tests. But who are the individuals here? How many points are there? There are 51 points, one for each state and DC. Do states take the SAT? They do not. In our mind, when we say, given the critical reading score, can you predict the math score? In our mind, we are imagining the individuals to be test takers, students, not states. So while it is true that there is a very tight relation between average critical reading scores and average math scores in the different states, if you look at individual students, for example, at this state, would all the students have scores at this point? They would not. On average, this would be their reading score, and on average, this would be their math score, but their points would be a blob with this as the center. If you replace this point of averages for each state by the cloud of points for the individuals in that state, then the cloud would be a fuzzy blob around this point, and you would get 51 fuzzy blobs. and the entire picture would therefore become fuzzier, and there would be a much looser correlation, much looser relation between the reading and math scores. What has happened in this picture is, by taking everybody in this state and lumping them all into this point, we have artificially introduced clustering. And therefore, of course, what we see about the degree of clustering is very high. So when you are trying to use a correlation to understand the strength of the relationship between two variables, and you've done everything you're supposed to do, you've drawn the scatter diagram and so on, think also very carefully about the individuals on which the variables were measured. And if the data were aggregated in any way to come up with the points, then be cautious in interpreting correlation. The main use of correlation is in predicting one numerical variable given the value of another. That's the topic of the next part of the course.